Okay, well, let's see here. Thank you. Okay, first off, I was gone Friday afternoon through like late Sunday, so I'm behind on getting your projects graded. My goal is to get that done by the end of the day today. Since it's this late and it's my fault, I'll probably push the final deadline back a little bit to give you the weekend over it. So no sense you have to suffer over my shortcomings. I had, as you noticed, we have jumped to Module 6, but Chapter 9. I purposely skipped the wireless LAN stuff. I want to take the chapters out of order a little bit, do the stuff that we're going to deal with, basically just reviewing technologies and looking at how they're used and things that are purely textbook. Oh, great. Purely textbook, I want to do first, and then get back into the ones we're going to dig deeply into, which basically comes down to 802.11 and particularly the more recent versions of 802.11. So I wonder if we're going to be able to do this. Close. Thank you. Sorry about this. I cannot figure out why this keeps deciding to do this. Okay, so what we're going to start in on today, and we'll finish up on Friday, are wireless metropolitan area networks. You've studied wired LANs, and we can characterize those as all of the ones we use anyway. All sharing. Excuse me. Yes. No. We can characterize these as sharing a couple of characteristics. First off, what we're talking about are systems that are limited in distance to about 100 meters of cable. That's just, almost everything we talk about now uses Ethernet. Current Ethernet is limited to 100 meters of cable. We can also talk about them being fairly fast. Okay? The problem comes when we need to extend a local network to multiple sites. If they're around the world, it's no big deal. We have to go through an ISP. But what if they're fairly close by? For example, what if we are in Paducah and we have 3 sites around the Paducah area, 3, 4, 5 miles apart? We can do it with carrier services. That's historically what's always been done. The carrier services, of course, are lease lines. You pay for them by the month. You select a data rate. You tell them where that link needs to go, and they make it come out on the other end. The downside is you have upfront cost with doing it, and you have the monthly expense of leasing that service from them. Now it works, and we can use these, some of these technologies we can use directly. For example, I can buy a pair of T1 muxes, and I can connect them with twisted pair, and I can build my private connection. It'll work just fine up to about 6,000 feet because that's the specification limit. T1 without a carrier infrastructure, read that without repeaters, without higher orders of multiplexing, has a distance limit of 6,000 feet. If I need to go faster than T1, which is 1.5 megabits, most of your drops in wired networks now are going to run at 100 megabits, so we're talking a little less than 2% of the data rate. That's a pretty big drop. If we want to go faster than that, we can go to a T3, which is still only 44 megabits. Our price goes way up if we do it as a lease line. If we do it as a private line, the big problem is, guess what? We've got, and I've even got to look at my notes because I've never even implemented one of these. We have a distance limitation of about 500 feet, a little less. So how do carriers do it? Well, remember what carriers are in business to do. Carriers deliver services to lots of customers. So this problem of taking bandwidth, particularly in our world, what we're talking about is internet access and moving it to multiple sites. That's what this basically is morphed into in 30 years. We call it the last mile problem. And the reason is the core of the internet are all commercial grade links. You know, they're running at gigabits and all of that. It's getting this last mile or two of the link to the customer that's a problem. And if we are trying to link multiple sites in a metropolitan area together, then we've got this problem several times over. You know, do we want to link those multiple sites in a single metropolitan area together in a LAN or an extended LAN? Well, if we do, then we're talking relatively high speeds. You know, you can see what the lease line cost would be to support the type of service that users have mostly come to expect. You're going to have to get into the optical carrier. The bottom three lines there, OC3, OC12, and OC192. Your text doesn't even want to take a shot at an OC12 or an OC192. An OC3 is going to cost you $10,000 to $30,000 a month. It's a lot of cash. We're probably not going to do that. There are alternatives out there for wireless, and those are, of course, this being a wireless course, are what we're going to look at. Let's finish defining the problem here before we go any further. If I want to do a lease line solution to this, then realize what the carrier is doing. We are paying the carrier to provide that bandwidth. So what they do is build a large infrastructure to get around the problems I've already mentioned. You know, distance limitations, and specifically distance limitations that increase greatly as our speed goes up. You know, by the time we're getting up to useful speeds, our ability to push a signal across media goes way down, and that doesn't matter on the media. Fiber is less of a problem, but it's still a problem. You can't send a signal forever in fiber. You know, if you're using multi-mode fiber, you're looking at, for high megabit, low gigabit speeds, you're looking at several hundred feet on fiber. If you're using single mode, you can go a long distance, you know, 50, 60, 100 kilometers, but it's expensive to do that. And guess what? You physically have to purchase the cable to do it, of course, but you also have to get permission, pay somebody for right-of-way. I have to get permission to run my cable across other people's land. And unless you work for a power company or a local government or a, let's see, who else would it, railroad, those are the only ones I can really think of that typically have right-of-way already, then you're probably not going to already own it. So between the cost of right-of-way and the cost of building the infrastructure to support the needs, the speeds that we've come to expect for our services, doing it yourself usually isn't a good solution. Carriers, of course, are doing this for multiple customers. I have a lot of customers going down, you know, Highway 100. And so I'm going to build an infrastructure out on Highway 100. I'm a carrier. I'm going to build an infrastructure out that supports very, very high speeds. So I'm going to spend a lot of money doing it. I'm going to buy right away. I'm going to put fiber out there. I'm going to put redundant links in the form of fiber rings. And I'm going to run drops to my customers that run at something slower than that. Is all that expensive? Darn right it is. It's hugely expensive. But I'm sharing that cost across multiple customers. So for me, it's affordable. I'm going to pass that cost on to my customer. If I'm trying to do it as an end user, I probably can't justify it. So the problem we get into here in this last mile issue, if you're near this infrastructure, that's great. If you're further away, you're out past where that infrastructure is built, you typically end up with one of two things going on. Either you call whatever carrier it is or carriers, and they say, okay, yes, we'll be glad to build it. Your one-time upfront cost is going to be, and they'll shoot you some huge number. What are they charging you? They're charging you the cost, or at least a significant portion of the cost of actually building this link out to you. If they don't see the potential for other users out here, you're going to take most of that cost as your installation. They're not going to take a risk on other customers maybe coming along later. So that's one problem. Second thing is they may simply just not want to do it, period. You know, they may not see it. In both of those cases, we can use wireless to overcome this. Provided I can get a path for the wireless technology, I solve the right-of-way problem. The law says I cannot charge you for passing a wireless signal over my house. It's not the same thing as digging a trench through my yard. We're not doing the same thing. If we were, I'd retire right now. I'd charge everybody in the world for using my house to deliver cell signals. But, you know, the law says we can't do that. So we get around those costs. Also, provided the path is in place, technology's come a long enough way that I can actually get these kind of speeds across a reasonable wireless link and spend a whole lot less money than this. Your textbook uses an example, and I forget the exact numbers, but it's something like a 15-mile link, and they compare looking at fiber versus using one of the wireless technologies. The wireless isn't cheap. It's in the realm of $20,000 or $30,000, but it pales in comparison to running 15 miles of fiber. Okay. So what we're going to look at are wireless means of dealing with this. And we're going to spend today kind of doing an overview, so I didn't actually mean to have that one pop up first. Last mile options for wireless break down into two systems. Optical systems, which are exactly what you think. They use light. They're essentially, the current versions of them are essentially fiber systems that just don't have a fiber. They take lasers, they modulate them. Instead of injecting them into a fiber, a guided media, they inject them just into the atmosphere, an unguided media. And we'll use lenses to collect them. A lens, from our point of view in wireless, is basically an antenna that operates at optical frequencies. The same fundamental principles apply. You know, the larger the lens, the greater amount of light we can collect, all of that. Most of these systems also, they all kind of look similar. If you look at the bottom picture there next to the word FSO, which stands for free space optics, by the way, that's the current term for these systems that use light through the atmosphere. The older term was atmospheric wireless systems or atmospheric laser systems. You may see that referred to. FSO is the current term. You'll notice in this picture and in any of these you look up, they all look pretty similar. They have a big central eye. That's a lens. And it's used just like you would use a lens in a pair of binoculars. It's used to collect more light and concentrate it in a smaller area. You also typically see multiple lasers. Now, these are there for a couple of reasons. You can run multiple links simultaneously across this. More commonly, what those are used for, the real problem with optical systems is you get an effect called scintillation. And scintillation, you ever notice the stars twinkling at night? What's happening is the air between you and the stars changes density, and the change in density refracts the light. So you end up with the light moving a little bit. You get some dispersion. For data links, that's a problem, because what I'm doing is changing the path and the timing of the pulses coming across that link. So how do multiple lasers help that? Well, the pockets that a laser passes through are pretty small. By using multiple lasers, I can say, well, I'm going to use these four, and they're physically separate, so the odds of a pocket of high density or low density passing in front of all four is pretty small. And so I can recover that using multiple lasers, and that's what you see going on. Optical systems obviously require an optical path. You know, you have to be able to stand at the transmit end, pull up a pair of binoculars, and see the receiving end. That's how they work. To the point, the way you line these up, it's a little hard to see in this room, but there's actually a telescope built into this. And you set these things up on a tripod, and you literally look through it, and you have a crosshair that you point at the other end. And they work great. You flip them on, up they come. I used to use one, it was an analog version, but I used to use this exact technology when I was in broadcast. We did, it was called second unit services for ABC Sports. We did the Indy 500. Well, our client, which was one of the Japanese networks, wanted a camera across the track. Okay, let's see. 30 Indy cars running down this track. We're not going to run a cable. They won't let us run a cable across, of course. So the only way we could get a link across was to use wireless. And this is exactly what it did. Worked beautifully. So these systems had been around a while. That was probably more years than I care to count, 20, 30 years ago. They basically updated them and made them digital. They carry high-speed data now. The physics are the same, and they work. They're good. You can actually push them out 5 miles if everything is working perfectly. More commonly, you're looking at something like a mile to a mile and a half maximum. You're not going to be able to get 5 miles reliably out of this. Interestingly enough, the place you see these used a bunch is to get across streets in major metropolitan areas. You know, I started business in this building. I rent space on the top floor. I need to expand. There's no more space in my building. I go down the street or across the street or what have you, and I have another link there. It may be 300 feet. I can do this without paying a carrier. You're not going to get right-of-way to run cable in a city like that. And so I can do this link and be in good shape. From a security point of view, it's a mixed bag. These are relatively secure in that you have to intercept that light, and this is basically a laser. You know, so take a laser pointer, and you basically have to be right in front of it to be able to decode it. If somebody is in front of it, odds are they're going to cut it off anyway, so you'll know it's there. The downside is, like any wireless system, you're putting your data out there. So there are considerations to be had there. Okay, the other big division, of course, is RF-based systems, and this is where we're going to spend most of our time. Now, this problem has been around long enough that we actually have several systems out there, and I'll give you a state of the world statement at the end of this after we look at the individual systems. The original problem with this actually dates back to the 60s and 70s when cable TV was coming along. Cable TV, of course, was put into place so that I could put, I'm in an area where I don't get good television reception off air unless I spend a lot of money on a tower and an antenna and all that. And so what cable systems would do is they would put up very tall master antennas to receive, you know, and here Murray actually has one of the oldest cable systems in the country. The first one started in 1963. We'd get Paducah, we'd get Cape Girardeau, we'd get Nashville off air. Cable would run them, would then bring them in, you know, they'd pull them off air on a big antenna, they would put them on coaxial cable and distribute it throughout the city. You guys have seen all that. Think about what you're doing. You're taking one signal off air, tall antenna, so I get a good reception. I'm running it through an amplifier. I'm increasing its power to where I can overcome lost through that coaxial cable, and then I'm putting it into shielded media and distributing it to my customers. Okay? That was the whole idea behind cable. What's the cost in doing that? I've got a huge physical cable plant. And this last mile problem, once I build out the easy houses, you know, the ones where you, and they literally looked at a statistic called houses passed per mile. And they had a break-even point. We need to pass this many houses per mile for this to be economically feasible. Very similar calculation is used right now by internet service providers. So what cable systems would do is they would see, once they got past that point where their break-even on houses passed was there, they'd stop building the system. So if I lived another mile out, I'm not going to get service. We have the same sort of issue with our data services, so you can see the parallel idea. The solution in those days, this is pre-internet, pre-high-speed data, was to use microwave systems to replace that cable. They would take the television signals, modulate them on a microwave system, put them through a microwave transmitter, and put set-top boxes at everybody's houses. And you know, channel A would be channel 6 out of Paducah, channel B on my set-top box would be KFBS. You can do the same thing now with data systems. Okay. So what they did, the early version of that was something called LMDS, which is a local multi-point distribution system. Get over my correct notes here. And the version of this that was most frequently used ended up with 155 megabits from the network towards you and 1.5 megabits coming back. So it was an asymmetrical service. Why would you do that in a data system? Think about what they're replacing. That was primarily designed to deliver television programming to you. So I need a lot of data towards you to deliver video, audio, all that sort of stuff. I don't need a lot of data coming back. You could argue you wouldn't really need any, but in those days, you know, they were looking at interactive ideas. And so they gave some bandwidth coming back for billing services. You know, I could select channels, things like that, across the control link. Asymmetrical data, they were set up in with a central system. It was basically a cellular system. Central transmitter, lots of customers using that same central transmitter. They used frequencies way up there, about 26 gigahertz to about 31 gigahertz. The problem with that, there is a thing called rain fade. Rain fade, if you've ever been watching, you ever watched like a DirecTV dish when a big rainstorm came along? What happens? Yeah, you'll watch it anymore. You know, football players turn from football players into collections of squares, and then they just stop. What's happening is, once you get up past about 10 gigahertz, the effect actually starts being a problem about 1 gigahertz. But at 10 gigahertz, a raindrop's a pretty significant portion of a wavelength. And by the time you get up to 26, 27, 30 gigahertz, it's, instead of being a fraction of a wavelength, it's several wavelengths long. You get a lot of absorption. You're heating the rain cloud up with your radio signal. What happens is you don't get, your path loss jumps way high. Fade margins in those systems are typically operated in the 25 to 35 decibel range rather than 15 dB because you have that much variation when a storm comes through. Pretty high speed down. The problem was the range on these was about 5 miles. Useful, coupled with the fact that it was asymmetrical, it wasn't great for business use as my data delivery. Useful, but not hugely useful. The updated version of it was something called multi-channel multi-point distribution system, and it was actually designed as a data system, but again was designed with the idea of delivering digital television. They in fact called these wireless cable, or what both of these were referred to that way. It's again a central transmitter cellular type system. The difference is MMDS can push out to about 30 miles, and it had useful data bandwidth at that point. It would move 1.5 to 2 megabits out to 35 miles. I could do faster links closer in, 40 megabits. In that last mile scenario, 2, 3 miles out, I can deliver T1. This is at T1 rates, you could run this system symmetrically. So I could replace my lease lines with the radio link. I still have to go through a carrier because this is a licensed system, but their cost is a lot lower. So my cost for my lease line is lower. Okay. Your book goes into gory detail on these. I'm glossing over them because you will never use either one of these two. They're kind of interesting from a historical point of view, but that's about it. The one you hear recently was WiMAX. This is 802.16. WiMAX was specifically designed as a data delivery service. It was not cable TV, although you could certainly move video over it. It was designed to give useful data bandwidth to both fixed and mobile stations over a pretty long distance. I'm going to glance up here and make sure I get my numbers right. It was designed to deliver 30 to 40 megabits at distances up to about 30 miles. Now, shorter than that, I can deliver a lot faster. I can deliver gigabit links across this. The protocol supports gigabits. I'm not going to do that very far, but I might do it over a couple of miles. Okay. So WiMAX, again, is a carrier-based service. I actually can purchase it as a private, as a company, and use it directly. The problem is I have to get the spectrum, and the spectrum is not in those license-free bands. It's spectrum that you have to license. So you're probably not going to get it. You'll get it through a carrier. Now, the issue with WiMAX is that 30 to 40 megabits. Anybody in here have LTE? How you like it? Yeah, LTE on your cell phone. How you like it? How's it compared to 2G or 3G? Yeah, it screams. Why would I pay WiMAX for 30 to 40 megabits, where for the same price or probably lower, because I'm selling it to everybody in the country, I can go do LTE, which is what's happened since this book was written. Okay. Your book covers cellular as a wide area net technology, and we'll look at that. We're going to look at it more from an application point of view rather than a technology point of view. This is a world changer, and this has happened in the last couple of years practically for our world. You've gotten a deployed cellular system where I can go out and buy a USB device, plug it into my router, and use it as a routable port into the network. Why am I going to mess with this? I'm not. Yeah. So that's the world changer that's come in. WiMAX is still out there. It's still a good technology. We actually have a graduate of this program, a guy named Wes Kerr, coming in. He's coming in for homecoming. He is deeply into broadband wireless delivery. He works for Connected Nation, which is a policy organization that looks at the availability of broadband data as an economic development tool. Now, that's boiling a very huge organization down into a very short sentence, but their goal is to get broadband data available everywhere. Okay. He has done a ton of work with WiMAX. The major part of what he does are propagation studies. You know, if I put a system this many feet off the ground in Murray, Kentucky, where am I going to be able to distribute signals to and how fast? He's basically doing the math that we're talking about here. And I'm going to have a long conversation with him about what's happening in this world right now. Stepping away from the textbook for a second, I wanted to cover this chapter because you will hear these terms, you'll hear WiMAX. People are going to continually ask you about this because it just seems to make such good sense. Well, why don't we just build our own system? Okay. What do you want to do? This comes basically down to the problem we defined early on. Where do you want the energy to go? How fast do you want to move data, which in our world translates into how much signal do I have to deliver, right? Broader band systems require more, faster systems require more signal delivered than simpler systems because the waveform is more complex. So what we have to do with that question is, does it make sense for us to build this infrastructure ourselves, or do we need to go through a carrier? And there's not a right answer to that. What are you trying to accomplish? If you need to push out a lot of data and you can afford the cost, which it's probably going to be less expensive to use a carrier, why would you use a carrier? It's easy. I plug a modem into my router. What's the downside of a carrier? If the carrier's network fails, your network fails. Now, you may not think that's likely. I was here for the ice storm in 2009, and all the carriers failed. Even the ones that worked only worked in some areas. If you were an AT&T customer, you didn't get anywhere. If you were a Verizon customer, you maybe could call some. So if I'm basing my business on that, I'm taking a chance. What am I going to do? Well, I'm going to look, as a network designer, I'm going to look at it and say, well, if we're going to use this as our wide area net backbone, or for our mobile data access, we may want to diversify and have two options on there. In other words, it's not as simple as just going out and buying a service. There's a lot to consider on that. When we look at wide area net technologies, that's primarily the focus we're going to take. We're geeks, so we like knowing how things work, but practically, I don't really need to know how my cell phone works to use it, you know, and that's what you get into when you're dealing with carrier wide area net technology. We're not going to implement the network. We're going to use it. We're going to attach to it. Now, we need to know what the capabilities are, but we got to apply some common sense to that too. And since this is a telecom management program, we also have to look at the business impact. How much does it cost me? You know, what are my options from a financial point of view? Okay, and what does more money buy me? So, and that's why I'm kind of going through this section fairly quickly. We'll do wide area net. Similarly, 321 digs into the technology behind cellular a lot more. We're not going there very much. What we are going to do, and I realize I've gotten off topic here and going on a little more. What we are going to do for the last part of this semester is look into the system that you will be building, which is the wireless LAN system. They're not terribly expensive. They are heavily, heavily used. So we're going to spend most of our time there. I do want you familiar with these systems. I want you familiar with the considerations, and that's why we're going through them at all. Okay. Questions over this was a quick overview through about the first half of the chapter. Friday we'll dig into WiMAX a little more. Even with my caveat about LTE replacing it, WiMAX has some advantages in some application areas. So we're going to take a look under the hood and see how WiMAX works. Let's see, where was I going? I'm having a senior moment. Sorry about that. Oh, the stuff I put up on on Module 5 is primarily vocabulary and technology questions. You'll have very similar stuff on this that I'll get up, and I'll make it due into next week. I'm trying to get us back in sync so that you're doing that stuff while we're doing the class. There are, in this class, really three kind of levels that I teach to. One is familiarity and discussing. That's what we're doing here. I want you to know the terms. I want you to kind of know how to use them so that you can discuss these things at least to the point of view of understanding what somebody's proposing. Then you can go back and read and see how the specifics of it apply to your situation. The next level up is stuff that you really do need to understand that you're probably not going to implement. For example, the wide area net carrier stuff. You need to understand what its capabilities are so you can make good decisions on it. I doubt if any of you will use this kind of technology. I doubt if any of you use that. I know you won't use LMDS. You almost certainly won't use MMDS. And probably you're not going to use WiMAX. You might run into them and have to use them. Free space optics, you'll probably use. But they're also pretty simple to use. Wide area net stuff, you have to know what it's going to do because it is the cloud in the middle of all your sites. So that's the way I'm approaching that one. The last one is the one that I really want you to be able to do, dig, and actually implement, and that's the wireless LANs, which is why I moved it to the back. We'll spend the last part of the semester there. Okay? We'll see you Friday. If you haven't read Chapter 9, please do so before Friday, and we'll dig deeper into that idea.